Hello guys, today we are going to talk about real numbers, an introduction. Now let me share my screen. Okay, so real numbers. What are real numbers? Real numbers are the numbers that you use in day-to-day life, right? All the numbers that you use in day-to-day life. In daily life, right? For example, 1, 2, 3, these are real numbers. Even 1.5, 1.73, negative 16.87, all those numbers are real numbers. And even numbers like this, they are real numbers. So all the numbers that you know of, except there are numbers called complex numbers. We'll talk about them later. For example, square root of negative 1. So things like that we call complex numbers, where you get the famous I and those things later. Now, there are different, we can break real numbers into several categories. So, real numbers include natural numbers, whole numbers, integers, rational numbers, and finally irrational numbers. Now, what we are going to do today is to talk about these things. Now, natural numbers. Natural numbers are actually the numbers, these numbers. Why it's so natural? That's how we started everything. That's how the mathematics was started. 1, 2, 3, 4, 5, using your fingers, you start to count. So those numbers are natural numbers, right? Now, as a set, we use the letter N with a double line with like this. And we start with, normally we write down a set inside curly parentheses. So 1, 2, 3, and forever. That's the set of natural numbers. Now next, whole numbers. Whole numbers, it's exactly like natural numbers, but with one more number, 0. 1, 2, 3, 4, 5, and so on. Now the 0 was included into the number system later, so that may be the reason why it came like this. Anyway, whole numbers we use W's. Again, W with two line W on this left side, and inside curly parentheses 0, 1, 2, 3, like that. Integers. Now integers are, well, integers is much larger than whole numbers. Integers, okay, let me first write whole numbers. 4, 5, 6, and so on. Integers, you also have negative numbers. So negative 1, negative 2, negative 3, and so on. We use the notation Z with again a double line like this. So how do we write down this inside a parenthesis, curly parenthesis? Now we have a problem. Unlike in previous cases, there is no starting point. So you have to put some dots because it's coming from negative infinity. And negative 1, 0, 1, 2, and so on. You can do it like that. Now certain books use the letter I for integers like this with a double line. Well, I like to use C because it's I believe that's standard, more standard. Now, rational numbers. Rational numbers are any number of this form. Numbers, a number of the form A or B. A can be any number. A can be any integer. Sorry, A is an integer. B is also an integer except 0. B cannot be 0. Why? Because you cannot divide by 0. Now let me go to the next page because we don't have enough space now. Rational numbers. So example, so we are under rational numbers. Let me call it rationals. Examples, 3 over 5. Is it in A or B form? Yes, right? A is 3, B is 5. And remember, A has to be an integer. Normally we write it like this. A is an integer. This notation means belongs to. It's easy to learn mathematics when you know these notations. And using that notation, B is an integer except 0. So we can write it like this in a more abstract way. So another example is negative 3 over 8, 5 over 12, or 173 over negative 2. All these are rational numbers. Now I have a question for you. Is this a rational number, 5? Well, at first you may think no, because it's in this form, but if you look at this carefully, 5, you can write 5 as 5 over 1, right? So yes, A is 5, B is 1, which is not 0, yes, so that is a rational number. So which means every integer, negative 8 over 1, right? So every integer is a rational number. That means rational numbers is much bigger set. It includes every integer. Now let's go back to the, now look at these natural numbers. So I just said every integer, all these guys, they are rational numbers. They are inside this, right? So every integer is inside this. And if you think about whole numbers, any whole number is an integer, so it sits in this. And natural numbers, any natural number is a whole number, so it sits inside this. Now, let me go to a new page. If we use a Venn diagram, in set theory we use Venn diagrams. If we use a diagram, it's easy to understand this. Let's say these are natural numbers, so 1, 2, 3 and so on. Whole numbers contains all the natural numbers and one more number, so W, you have 0 here. 0 is the only number that sits between these two boundaries, because 0 is the number which is a whole number but not a natural number. But on the other hand, let me see what is the next number in next set of numbers, integers. So integers right here. So what are the things that I must include in between these two? Let me use different colors. And what are the numbers that I must write down between blue and yellow? All the numbers which are not whole numbers but integers, those are negative numbers, right? So negative dot 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 dot, negative 3, negative 2, negative 1, all those numbers. So there are infinitely many numbers here in this region. And then rational numbers. Every integer is a rational number. By the way, I forgot to tell you, we use this notation Q like this for rational numbers. So rational numbers, there are millions of, infinitely many numbers. There is no order, we cannot write it like a nice order. So all those things looks like this. They sits here. They sit here. So this is the distribution. And let me go back. And finally, rational numbers. Now, before we talk about irrational numbers, there is a little bit more to talk about rational numbers. So, still rationals. Okay, now rationals. Now, let's take two examples. Let's say 1/2. Yes, it's a simply rational number, right? Now, what is the decimal expression for this? That means you divide 1 by 2, 0, you borrow 0, 0.5, right? Now, let's take another. How about 1/3? Well, in this case, you borrow 391039103910. See, it keeps go forever. So we write it as either 3 dot 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 dot. Much better way, you write a 3 and put a bar. A bar means that you keep repeating that forever. Now look at these two. There is a difference. This terminates. This is non-terminating. No, does not terminate. Non-terminating. Even though it's non-terminating, there is a pattern. That's the key. What is the pattern? 3, right? So we call it a pattern repeats. Oh, it's repeating and non-terminating. Now let me give you more examples, then you'll understand. How about what if you had a number like this? Let's say 11, 4 over 11. Now if you divide this, okay, 4, 11, 0, 40, so 3, 33, you get 7, 70, so you have 6, 66, you get 4, 40, so 3, and this thing will keep repeating. So 0.36 forever. So 36, 0.36363636. So that pattern can be with two numbers like this, or it can be 0.7851 and 7851, 7851. So that's the pattern. So that can be of any number of numbers. See, if that happens, still it's rational numbers. So the key thing to remember, a rational number in decimal expression, two things can happen. Either it nicely terminates or repeats a pattern. So this is non-terminating but repeats. Now that set of rational numbers, this will give us irrational. The definition of irrational is simply non-rational. So what does that mean? That means a number that cannot be written in this form. Or in other ways, going back to this, when you divide a number by number, either it's going to terminate in the decimal expression or it repeats. But there are numbers, neither happens. So in this case, non-terminating with no pattern. Now, unless you see an example, you want to get this. So let me give you an example. Square root 2. This is, my memory is correct, 1.732. I'm not sure. You can use a calculator. The point is, this pattern will never repeat. So there is no pattern. So irrational numbers, a number like this number exists, right? For example, in a right angle triangle, if this side is 1, this side is 1, by the Pythagorean theorem, length of this side is square root of square, so that's square root 2. There is a number like that. But when you try to write the decimal form of it, you get set of numbers with no patterns, but it keeps going on. So those kind of numbers are irrational numbers. And the other property, they cannot be written in this form nicely, some integer over some integer. You cannot do that. So famous other irrational numbers, I mean, every square root of, if that is not a perfect square, that's going to be something like that, or pi and e, things like that. So we'll talk about these things later. Now the last thing that we are going to talk here, so we started with real numbers, remember? Real numbers, any real number, either that's going to be a rational or irrational. Now do you understand what I'm doing here? Because see, here, these are rational numbers. So rational contains integers. Integer contains natural numbers. Whole numbers. Whole number contains natural numbers. But irrational, if I try to draw this, I mean, this is not the perfect, I must draw irrationals much bigger than this, but since I don't have space, irrationals. Normally the notation, some books use I and some books use Q prime. There's a reason, because outside Q. So reals contain any real number, it is going to be rational or irrational. Inside rational, you have what are those numbers? Inside rational, rational can be broken into integers, and then inside, let me put it, inside integers you have whole numbers, inside whole numbers you have natural numbers. So I believe that's enough for today's lesson. So that is the breakdown of real numbers. Okay.